All right, let's work 10.11, which is more Lewis dot structures. We are asked to draw a couple Lewis dot structures for N3 minus 1. This ion is actually known as azide. And sodium azide is one of the active ingredients in airbags in automobiles, as it turns out. So that's kind of interesting. And then part B, they want us to write NO2 minus 1, which is nitrite, with the I-T-E ending. These are a little bit different than the previous problems because these are ions and not neutral molecules, okay? But we're going to approach things in largely the same way. We're going to start by counting number of valence electrons available. Now nitrogen, each atom has 5, 5, and 5, because it's N3. But I want you to be very careful and notice that these are ions. If you have an anion with extra electrons, you have to add that in. What that says is it's got one too many electrons compared to what the periodic table valence electron business would predict. Okay? So this azide doesn't have 15 electrons, it has 16. That's super important. Okay? You've got to be able to do that. If it's a neutral molecule, you just use your guidance from the periodic table. If it's a negative ion, you have to add back in electrons. You see how this is minus 1? You add what the atoms would give you and add, essentially whatever the charge is. Here it's minus 1. If it's positive, you take electrons away, you subtract them. Okay? You got to do that, or else you won't be able to get the right answer, right? Now we got 3 atoms of nitrogen. We're going to basically approach things our normal way, and that we're going to start by connecting the atoms single bonds. Okay? Like that, just to see if it works. Now we're going to want to complete our octets wherever we can with the 16 electrons we've got. So if I'm doing that in the central atom, I have to do 2 more here. 2 more lone pairs, okay, so 4 total electrons. And then I need to do, since these are single bonds right now, I would need to do 6 dots around the periphery. Because again, our guiding principle here is we want every atom to get to the octet, or having 8 electrons associated with it. They can be shared, or they can be lone pairs. So this one, for instance, 1, 2, 3, 4, those are its lone pairs. They belong to this nitrogen, that's 4. And then it also shares 4, 2 here and 2 here. So it's got 8. Similarly, with these 6 and these 2, this has got 8. Likewise over here. But I think there might be a little bit of a problem with this structure. If we add up the total number of electrons we used, let's see what we got. So here's 1, 2, 3, 4, 5, 6, plus the 2 from this bond, plus the 4 lone pair electrons, plus the 2 from this bond, plus 6 more. So how many total? Well, this is 8, that would be 12, 14, and 6 is 20. The structure I have proposed at first glance, my first draft, uses 20 electrons. I only have 16. Not going to work, right? So this is not the correct structure for azide. Got to modify it. Now, the next step in modification is figuring out how many more bonds I need. In other words, I need to share more electrons because I only have 16, and this one needs 20, so I need to share more to make more things happy with less electrons, so to speak. And again, the simple rule I gave you is find the difference between these two numbers. Here that would be 4, and divide that by 2, which yields 2, because 4 divided by 2 is 2. That tells you how many more bonds you need, okay? So I need 2 more bonds. I'm going to try to do here and here. I'm going to erase some lone pairs and see if this works now, okay? So I added a double bond here. I added a double bond here. Now for this nitrogen, it's got 1, 2, 3, 4. All right, and it participates in sharing 4 here, so that gives it its 8. It's happy. The central nitrogen's got 4 here that it can participate in sharing, 4 more here, so it's happy. So I'm going to add these 4 back in. And then likewise, the one on the far right here has 1, 2, 3, 4. 1, 2, 3, 4. So that's 8 total, with 4 being additional, these guys right here, okay? So it looks like with this new setup, for Lewis dot structure. I've got 16 electrons used. That's what I've got. Okay, so that meets the criteria for being an acceptable Lewis dot structure. Nothing exceeds the octet rule here. Everything is great. Now, what about formal charges? Assigning formal charges. This is again something that we want to learn how to do. Some of the other videos have talked about this briefly, and I just wanted to review the concept again, because formal charges ultimately allow us to predict what might be the best Lewis structure. Okay, now formal charge calculations, the number of electron minuses in the valence shell of our atom, and that's basically told to us by its position in the periodic table. And I'm going to subtract number of electrons assigned in the Lewis structure. And that's basically how I compute this, okay? So for this nitrogen right here, nitrogen always has, what, 5 electrons assigned to it in the periodic table. Now I got to subtract how many are assigned to it in the actual structure. So 1, 2, 3, 4, these lone pair electrons belong to this nitrogen, and then it participates in sharing these. Now, again, we're going to assume they're shared equally. So there's 4 here, so this one gets 2, this one gets 2. So it looks to me like this nitrogen participates in borrowing 6 electrons, or having 6 electrons associated with it, if I'm going to assign electrons. Okay, so that means its formal charge in this structure has to be -1, 5 minus 6, right? What about the nitrogen down here? Well, again, 5 is the periodic table value. It's always that case for nitrogen. And how many are assigned to it? 1, 2, 3, 4, 5, 6. So it seems like to me, this one's also -1. And I think that makes a lot of sense if you think about it, because the pattern of bonding 2 bonds and 2 lone pairs is identical on either end of this molecule. So -1, -1. Now what about the central nitrogen? Well, again, 5 from the periodic table. I subtract what's assigned to it. To me, right now, it looks like 4 electrons are assigned. Because remember, each one of the lines count as 2, but we're splitting them between the bonding partners. So 1, 2, 3, 4, essentially, for this guy, right? So that makes it +1. Formal charge on a central atom. If you add all these together, you get a -1 charge, and that's what we should get, because that's what we expect. When we calculate formal charges, if you add them together, you got to get the charge on the ion, okay? So this is a perfectly reasonable Lewis dot structure. Now you have to ask, is there any others that we could at least propose? What about 1, 2, 3, and 1, and ... What about this guy? All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I've used 16 electrons. That's consistent. And I think everything is complying with the octet rule. So that shouldn't be a big problem, right? So 16 electrons, octet rule satisfied. What about formal charges in all these, okay? So for this guy over here on the right, well, I'd have 5 minus 1, 2, 3, 4, 5. So actually that looks pretty good. Because out of 5 minus 5, I'd have a 0 formal charge. So that's good news. All right, so that's 0 formal charge there. Central nitrogen, 5 from the periodic table. I'm calculating formal charge here. Minus how many are assigned. It looks to me like 4 are assigned here, if I'm not mistaken, right? 1, 2, 3, 4. So 5 minus 4. That would have a +1 formal charge. And then finally, the one down here, 5 from the periodic table minus how many are assigned? Well, 1, 2, 3, 4, 5, 6, 7. Okay, so that's going to have a -2 formal charge associated with it. All right, now the thing is that the further that an atom departs from 0 formal charge, generally speaking, the worse it is for the structure being a viable thing, okay? So I might think the first structure is a little bit more viable than the second, okay? And it's particularly bad when a highly electronegative element has a positive formal charge. That's usually really bad, okay? But nonetheless, we can assign these sort of resonance forms of our azide, and then the last one that we can envision here might be something like this, right, where we reverse the location of this triple bond. So I'd have dot, 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 dot. And then that's got 4 bonds, so it's got its 8. And then down here I just need 2 more electrons. So basically we kind of flip where the double and triple bonds are. The formal charges would also be flipped if we were to calculate them. Okay, so these could be 3 possible Lewis dot structures for azide. So moving on to the next one then, we got NO2 minus 1. Follow the same exact protocol as before. Count valence electrons as assigned from the periodic table. Nitrogen would give us 5, and each copy of oxygen would give us 6. It's a minus 1 charge, so we're going to get 1 extra electron. So 12, 17, 18 electrons is what we can use. Pick the central atom. Nitrogen has the lowest group, so it's probably going to be our central atom. So I write it in the center, connect as much as possible, and then start trying to complete octets, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Oops, I've used too many. I used 20 and I only have 18. So that tells me I need another bond, right? So let me draw it in right here and see how that works. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oops, I'm going to get rid of these two. Okay, let me count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. This uses 18 electrons, which is what I have. So it's a perfectly allowable Lewis dot structure as a result, okay? Used 18, I had 18. That's good. Now, is this the only structure that I can propose? Probably not, right? Because maybe I can switch the location of where that double bond is to have a different resonance structure or a different resonance form while maintaining all atoms octets, okay? And the central atom nitrogen needs another pair of dots there, okay? So these are my 2 possible resonance forms. And again, if I go and I try to differentiate between these bonds in the lab, I'm not going to be able to do it. That's kind of the idea behind it. These bonds, as it turns out, would be identical, okay? They'd have a bond character of 1.5, and neither 1 nor 2, but both of them would be 1.5. And they'd be treated in the lab as if they were identical. And that's why we have to draw these resonance forms, okay? Because it's neither, in reality, the molecule is neither this one nor this one. It's a hybrid of the 2, and that's the whole idea behind this, okay? So now, what about formal charges, okay? Let's do the central nitrogen. As we talked about earlier, nitrogen's assigned 5 valence electrons by its position in the periodic table. And it looks like right now, I've got 5 assigned to it. 1, 2, they belong to this nitrogen, and then we get half of all the bonds, which is 1, 2, 3. So that's 5, so this has got a formal charge of a big fat 0 then, right? What about our oxygen? So let's do this one first. Oxygen, by virtue of its placement in the periodic table, has 6 valence electrons. And it seems to me that 6 are already assigned. 1, 2, 3, 4, 5, 6. Because remember, it shares half of these. So this oxygen has a 0 formal charge, the one that's in the double bond. And this is one reason why, again, why oxygen likes to form double bonds, or 2 bonds, really, to oxygens, and then have 2 lone pairs, because it gives it a formal charge. But the thing is down here on this end of the molecule, I'm pretty confident that we're going to get a -1 formal charge if we compute it. Because look, the whole thing has a -1, and I got to pick up a -1 somewhere. But just to confirm that, 6 is the number of valence electrons from the periodic table, and I subtract how many are assigned to it. It looks like 7 are assigned to it, right? 1, 2, 3, 4, 5, 6 lone pair electrons, and then half of what's in this bond. And again, remember, each line corresponds to 2 electrons, half of that's 1, so I've assigned 7 to it in this structure. Hence, this guy has a formal charge of -1. Okay, and it would reverse down here because we changed the location of the bonds, right? But nonetheless, another example of Lewis dots.